Paul made a point there. We're just trying to make very rough numbers in here, and that goes, to significant digits. Probably your answer was 3,172, right? But these are very rough numbers. What we're trying to go to the order of magnitude. We're trying to compare 1 day to 3,000 years. So for the sand, and if I extend the concept also to here, this is about 1 day, this is about 3,000 years. So that's a very long time. And if you have a lot of sediments coming on in a basin at a rate faster than the pore pressure can be relieved, all that pore pressure is going to be built up in those locations. And this is a huge problem in offshore conditions, especially in Gulf of Mexico. There are many places in which many of these mud rocks have been deposited, and more sediments came after that, and the pore pressure is locked in, and it's very high. And in some other cases also there are salt deposits. That salt also has a very low permeability and acts as a flow barrier that also locks in the pore pressure. And whenever you go and drill in a location like this with very low effective stress, the drilling is going to be very problematic too, because the rock around the wellbore is going to be very soft. Not very soft, but it's going to be very weak. And if the rock is weak, you're going to have problems with wellbore stability. It's not the same drilling a wellbore through a weak rock than through a very competent and strong rock. Okay, so let me do one more analogy that I forgot to tell you about, which is related to this. And then I'm going to talk very quickly about other mechanisms of overpressure, and we'll be ready for talking about horizontal stress next class. And the analogy is, when you load sediments and you don't let the fluid escape, that's something called undrained loading. And it's written like this. So undrained, and it means it's not draining loading. And you should think of this, if you think about this analogy of undrained loading and pore pressure dissipation, it's like if you're playing with mud, right? And you squeeze the mud, what happens with the mud? Can you, if you got a ball of mud, can you squeeze it down to a small size? You say yes, Mr. Tozer? A bit, but could you say you have like a ball of mud like this? Would you be able to squeeze it down, say, to 1/10 of its size? What's going to happen? It's going to probably go like kind of squirt through your fingers, right? That's because the mud is full of water. It doesn't let the water go out. It's not like a sponge. A sponge you could like, just squeeze it and reduce it to 1/10 of its size or more. But a mud, it has such a low permeability that it's not going to let the water go. So instead of that undrained loading is going to make the mud just go through your fingers, and it's going to keep the water. You will have to squeeze it and put some sort of a drain that lets the water move very slowly in order to get that to compact. And actually we do that in my lab. We squeeze rocks to make synthetic mud rocks. And sometimes it takes a day, a week, sometimes a month to do that squeezing in a very small piece of rock. Okay, so we have a few more minutes, 4 more minutes, and I'd like to talk very quickly about some other sources of overpressure. The one that we just saw, actually I never put a name on it, but it's something which is called, let's see where is the most appropriate place to put it. Here. this one is called, some people call it under consolidation, and in the geology literature is called disequilibrium compaction. It means a compaction that still didn't reach equilibrium because the solid didn't take all the load. Quite a bit of the load is taken by the fluid. So other sources of overpressure include changes of temperature. If you have a change of temperature, if you are burying a rock and it gets hotter and hotter, the rock is going to try to expand. If the rock cannot expand, it's going to build up pore pressure because of thermal dilation, right? So delta T is going to lead to thermal dilation of the fluids, of the solids, and thus going to end up in a change of pore pressure. So you guys, you can see that, right? I don't have to go a lot more in detail about that. Another source of overpressure is going to be hydrocarbon generation. So when organic rich rocks get into right conditions of pressure and temperature, you get either into the oil or in the gas window. And some of those organics are going to go into hydrocarbons, are going to convert into hydrocarbons. And those hydrocarbons are going to take more space than the organic. If you have a fluid that takes more space than what you started with the same volume, also you're going to generate pore pressure. This like, if you're boiling water and you have a lid, you add heat and the water converts into vapor. The vapor takes more space than the liquid water, and that makes the pressure to go up. And it's the same thing with organic rich rocks or source rocks. As you get to the oil and gas windows, some of those organics, which were solids, they start to convert into gas, into oil. They take more space, and the pore pressure increases. Actually, this is a very important phenomenon because many of the shales from which we're producing oil and gas right now, they have a lot of overpressure because of this phenomenon. And that's actually good, because if you have a high pore pressure, we say that overpressure is not very good for drilling, but for production it's very good, because if you have a high pore pressure, then it's much easier to drain fluids out of the reservoir. So probably we say this is very important for shales. If we want to go to the long name, this will be organic rich mud rocks in the oil and gas window. That will be a long description of what we nowadays call shale. And for this case, pore pressure is very important. Sometimes even pore pressure is that important that the pressure might be so high that it makes small fractures in the shale. And those very tiny fractures also help a lot for the fluids to get from very tiny pores to the wellbore. Another process is clay diagenesis. We're not going to go into detail about this one, but some clays and minerals metamorphose, and as they change, say from amoridonite to illite or to some other types, also they take a different volume, and as they do that, they also can release some water, and that water that before it was bound to the clay and then it's not bound to the clay anymore, also generates overpressure. I'm a little bit exceeded with time, and I'm missing one, but that one deserves a little bit more than 1 minute. So we're going to talk about buoyancy next class. Okay? So guys, remember that the homework is due next week. As I told you before, do the homework, do the problems in my class notes. Try to train before you take the exam, before you take the quizzes, and you said it's very easy if you do that. Yes?
Is it Tuesday or Thursday?
I think it's Friday? Probably Friday. Okay, yeah, I don't remember. If you go to Canvas, you will see the exact date and time over there. All right, guys. Thank you, and I'll see you next week. Oh, the extra points. Guy, if you want the extra points for answering the questions, just stay a little bit. Those that want it. Yes, you want to say something?